This meeting is being recorded.
Hello, my name is Lucas, and I'm here with...
Hi, I'm Jessica.
Hi, I'm Sally.
And we're going to be talking today about our final project for our class in Fundamentals of MRI and Neuroimaging Analysis. This is during our spring 2020 semester at Carnegie Mellon during the pandemic. And this project demonstrates strategies for investigating a human subject with a magnetic resonance imaging or MRI machine. In this experiment, we performed a full MRI and functional magnetic resonance imaging fMRI scan on a volunteer subject. Our analysis included structural segmentation, resting state, independent component analysis, or ICA. Our visual task investigates a spinning checkerboard pattern during the fMRI that activates the parietal and occipital portions of the brain, similar to the image or checkerboard pattern below. The scanning took place at the CMU Pitt Bridge Center, which is located in Pittsburgh, Pennsylvania. It's close to the CMU and Pitt campus. It's a 3T Tesla Siemens Prisma, and this is the what the MRI machine looks like inside. And it is a 60 centimeter or 23-inch regular bore, which is the area where the subject can fit inside. It's a 64-channel head coil with a transmit and receive bird cage with a less than 2 millimeter isovoxel, and there's also a less than 2-second repetition time that the machine is capable of. Overall objective of this study was to determine the importance of visual information related to motion perception in the presence of visual stimulus. We used bold fMRI to monitor brain activity while a subject was presented with a visual stimuli corresponding to a rotating checkerboard disc at a frequency of 1 degree per second. And we then investigated the neuroconnectivity in the visual cortex related to the occipital and parietal portions of the brain. The null hypothesis is that there is no significant difference between a spinning disc or no disc. And I will now turn this over to Jessica.
Okay. Now I'm going to talk about our experiment design. The process was first tested on a water phantom and then tested on our subject. There are 7 sequences, and each consists of 1 minute of visual stimulus, which is showing the video of rotating checkerboard, and followed by 1 minute of rest block showing a great blank image, and it repeated for 7 times, so it is 14 minutes in total. Next slide, please. Our spinning checkerboard is generated using a MATLAB code, and we use a demo from the SCARF lab. And the video of spinning checkerboard test was used in another code and screen recorded, so we can use it in our experiment. Next slide, please. This is our block design. There's 1 minute of stimulus and 1 minute of resting state, and repeated for 7 times. So the total duration was 14 minutes. And we use double gamma HRF in our GLM design. Next slide, please. We acquire our data using a Siemens Prisma 3T scanner with a 64 head coil, and the structural images were acquired using a T1 weighted MP range sequence with a voxel size of 1 cubic millimeters, and each volume took about 84 seconds to acquire for T1 and 91 seconds for T2. Next slide, please. We have 1 subject, and the subject is male, and he is 6 feet tall and 330 pounds. The subject was asked to look at the center of the spinning disc and then relax while there was no spinning disc. The subject wore earplugs and looked at a mirror above their eyes, so he could see the screen where the checkerboard was showing. And then Sally is going to introduce the result for us.
Hello, I'll be talking about outcomes. So first, we're going to be looking at the brain extraction, and basically this step was done so we can isolate the brain from the rest of the matter that is present in the MRI scan, including the face, neck, etc. So this step was used just to isolate the brain. On the left, you can see the T1 weighted images, and on the right, you can see the T2 weighted images. And we did this step so we can do the coming step. Next slide, please. So that step was to isolate the brain, and through that, we were able to classify the matter within the brain. And we were able to classify the cerebral spinal fluid, gray matter, and white matter. And the cerebral spinal fluid is represented in blue on both images, T1 and T2. The gray matter is represented in blue on the T1, T2. CSF is red. White matter is green on T1 and T2. So that's important for the visualization of all the different types of matter within our subject's brain. So next slide, please. Now I'll be talking about the statistical analysis, and I'll be starting off with the occipital lobe. So we did a feet Curie analysis through FSL, and we got like a bunch of statistics. We got the t-test, we got the p-value, we got the z-score, and specifically I want to focus on the t-test and the p-value. So the t-test allows us to determine if there are significant similarities or differences between two sample sets. And in this case, we're going to be comparing the resting state and the stimulus. And if you get a t-test value of 0, that means that there is no difference between the resting state and the stimulus. So we got a t-test value of 0.693, which shows that there is occipital lobe activation when there is stimuli, because there is a t-test value above 0. And that is indicative that there is a significant, or like semi-significant, not extremely significant, positive difference between the resting state and the stimulus. We also, unfortunately, got a p-value that is above 0.05. The p-value being 0.05 or below means that our data is statistically significant, but we got a p-value of 0.1517 for the occipital lobe statistical analysis. And below, you can see a picture of the occipital lobe mask. Next slide, please. And now we'll be talking about the parietal statistical analysis. So again, we're going to be talking about the t-test. In this case, we got a lower t-test score, which means that there is a slight correlation between parietal activation and stimuli. But it is not as strong of a correlation as the prior t-test value. And this means that there's a difference between the stimulus and the resting state, but not a large difference. Luckily, the p-value for the statistical analysis was below 0.05, it was 0.03, which means that our data for this was statistically significant. And you can also see the parietal lobe mask below. Next slide, please. Now I'll be talking about where we went wrong or things that we would change. And this could be the cause of some of the p-value and t-test scores that we got that I went over in the previous slides. So in the future, we would include a crosshair. This is something that was brought up to us by our subject. Having a crosshair in the transitionary period would be beneficial. We would also like to use an eye tracker. An eye tracker would increase accuracy. There was also an error in the screen during the transition that was reported to us by the subject. In the transitionary period, there was a green flashing screen, and this could cause for errors in our data as well. The subject also noticed that there was a cursor on the screen during the resting state portion. And This has a large potential to make error, because during the resting state, we want our participant to be looking at nothing, because we want it to be between like activation and no activation. So having the participant seeing a moving cursor allows for parietal and visual cortex stimulation that we maybe would not want. So that is something that we would change in the future. And another reason why we got errors, or why maybe our t-test score wasn't as high for the parietal lobe, and could be persistence of images. And persistence of images occurs because the subject sees like an image for a long time, and then after the image goes away, it still appears in their retinal view. And this causes error because then it's not as much of a difference between the resting state and the stimulus if the participant can still see the stimulus during the resting state. So in the future, maybe we would shorten the tasks so persistence of images doesn't occur. And of course, we would like if we could increase the sample size and have more subjects to acquire more data from to increase accuracy. Thank you very much. I'll be passing it back to Lukas.
Okay, thank you, Sally. In conclusion, we have over 200 hours of combined team work that has been recorded and logged. We scanned on 6 different days. We included the structural segmentation, resting state, and independent component analysis. And I would like to thank you for your time. And here are our references.